In this video, we're going to be talking about elementary matrices. These are special types of matrices that we use to carry out matrix multiplication. There is one key idea in this video, and that is that when we do standard row operations, what we are actually doing is a form of matrix multiplication. So let's begin by recalling the kinds of operations that we do when we do row operations. One of the things that you do is you can interchange two rows. Or you can scalar multiply a row, as long as your scalar is not 0. And the last type of row operation that you do when you're, say, putting a matrix in reduced echelon form is adding a multiple of one row to another. So I'm going to show you how each of these three row operations are matrix multiplication by way of example. Let's start by taking a look at a simple 2 by 2 matrix and then performing a row operation. There's really only one interchange of two rows when you have a 2 by 2 matrix. That's the interchange where you send row 1 to row 2 spot and row 2 to row 1 spot. How you can do this particular row operation with matrix multiplication is to multiply on the left by this special matrix, 0, 1, 1, 0. What 0, 1, 1, 0 looks like, by the way, is as if you started out with the standard identity matrix, but then you interchanged its rows, so that you had 0, 1 appearing first and 1, 0 appearing second. Now, there are only 4 dot products to check, and it's easy to see that if you take 0, 1 dotted with AC, that's going to give you C, the first entry. And if you take 0, 1 dotted with BD, that gives you D, essentially putting the second row in the first row spot. And then you would get the other entries here, A and B, by carrying out the other 2 dot products that are prescribed by matrix multiplication. Let's now look at a 3 by 3 example. So now what I'm going to do is take the 3 by 3 matrix ABC, DEF, HIJ, and I want to perform the row operation that sends the first row to the third spot and the third row to the first spot. Well, this is going to be a similar matrix multiplication. Now I'm multiplying on the left by this matrix. And what this matrix looks like is as if I had started with the usual identity matrix, but then flip-flopped the first and third rows. And lo and behold, when I carry out this matrix multiplication, there are 9 calculations to do, I do get the correctly permuted matrix as the result. So both of these matrices that I'm using that I've circled in green are what are called permutation matrices. A permutation matrix is one which you can think of as being formed from the identity matrix, where some of the rows have been permuted. And it's not just this particular row operation where you interchange the first and last rows being carried out by multiplication by a permutation matrix, but any row exchange or any permutation of the rows is carried out by some left multiplication by some permutation matrix. So this explains the first type of row operation, interchanging two rows. Let's now look at the second row operation, which is scalar multiplication. All right, let's go to a new page in order to take a closer look at this operation. I'll have a 2 by 2 example and a 3 by 3 example. So for our 2 by 2 example, let's take our matrix A, B, C, D again. And now let's see how we produce 3A, 3B in the first row, which is the row operation that multiplies the first row by 3. Now we want to multiply times the matrix on the left, 3, 0, 0, 1. And this matrix is also formed out of the identity matrix. It looks like an identity matrix, except that in the first row, instead of having 1, 0, we have 3, 0. And you can see that this carries out the desired row operation. Let's look at a 3 by 3 example as well. Here's the same 3 by 3 matrix. And now let's see what happens if we put a scalar of square root of 7 in the last row. Well, A, B, C, and D, E, F are going to be unaffected. When we do all of the little dot products that form the matrix multiplication, the first 2 rows are unchanged. But the effect on the last row is that everything will be multiplied times the square root of a 7. So this type of elementary matrix is constructed by scalar multiplying a single row of the identity matrix. We have one more row operation to discuss, and that's adding a multiple of one row to another. So let's go through one example a little bit slowly. We're going to take our matrix ABC, DEF, HIJ again. And now we're going to left multiply times a matrix that looks like the identity matrix, but I've modified it in a third way. I have changed one of the entries off of the diagonal from a 0 to a 2, which is the highlighted entry. And now what happens when I do this matrix multiplication? In the first row, I'm going to get A, B, C again, because I have a series of dot products that look like 1 times that entry plus 0 plus 0. So this is going to give me an A, a B, and a C. Now, what happens when I work out the new second row? Well, from that dot product, I see that I'm going to get 2A plus D. Let me give myself a little bit more room with which to work here. And then I'm going to get 2B plus E. And following along, I'm going to get 2C plus F. And then the last row is unchanged, H, I, J. See, what's happening here is in the second row, I'm describing a particular linear combination. That linear combination is twice the first spot, plus once the second spot, plus 0 the third spot. And what those spots are going to be the entries as I move down a column of the second matrix. So that's why I see, say, a 2A plus D plus 0H occurring in this entry. The elementary matrix on the left is a recipe for carrying out the row operation that adds a multiple of one row to the other. So here's another example. Let's look at our matrix again, but we'll multiply on the left where we have used the identity matrix with a 7 in the 1, 3 spot. Now our recipe has changed. The recipe is that we're going to have 1 times the first spot, it's a linear combination, plus 0 times the second entry, plus 7 times the third. And when we work out this matrix multiplication, we see that's exactly what we get. We're going to have A plus 0 plus 7H. We're going to have B plus 0 plus 7I, and then C plus 0 plus 7J in the first row. The recipe that I see here describes what should happen to row 1, and the recipe falls in row 1. Now, the recipe that I see in the second row of my elementary matrix is 0, 1, 0. So this means just take one copy of the second entry from the second column. And that is what happens when I do matrix multiplication. So in other words, now I'm just going to get D, E, F back. And likewise, my recipe for the third row is just take the third row again, H, I, J. So this is the third type of elementary matrix that we see. And what these elementary matrices look like, the type of elementary matrices that add a multiple of one row to another, look like the identity matrix, but with a single non-zero entry off of the diagonal. Let me write down a kind of definition for what an elementary matrix is. So our definition for an elementary matrix will be a matrix that is obtained from the identity matrix by a single row operation. Elementary matrices can be thought of as a recipe for the row operation that is to be performed, which is exactly what we saw in the previous examples. An elementary matrix that looks like the identity matrix with a 2 off of the diagonal means that in that row, row 2 of what we apply this to will become 2 times row 1 plus 1 times row 2. Row 3 is going to become 0 times row 1 plus 0 times row 2 plus 1 times row 3, or just 1 times row 3. Every row of the elementary matrix is a recipe that describes the exact row operation that you want to perform. The same is true for elementary matrices that describe scalar multiplication or row exchanges. An elementary matrix that looks like a 5 and a 1 down the diagonal is going to carry out the recipe of 5 times row 1 and 1 times row 2. Let's now work through a longer example. What we're going to do in this example is we're going to take a specific matrix A, which I have written here. We're going to put it in row echelon form, and we're going to track the elementary matrices that we use as we go. So there's going to be a little bit of bookkeeping to do as we work through this example. All right, so let's do our first row operation to put this in row echelon form. That row operation is going to be -3 row 1 plus row 2 into row 2. That's the sensible row operation to be done. And as we do that, we leave the first row unchanged, we leave the third row unchanged, and then the second row is going to become 0, 2, 1. Now, there is an elementary matrix that accompanies this step, and we are going to take care to write it down. So the first elementary matrix that we use in this process is E1, and it needs to encode this row operation. So nothing happened to the first row, nothing happened to the third row. So we write down our standard rows that we would see in an identity matrix. But something did happen to the second row, and what happened was a linear combination of the form -3 row 1 plus row 2. So what we ought to see here then is -3, 1, 0. This row encodes this linear combination. All right, we've got more work to do before our matrix is in row echelon form. So it looks like the next thing to do would be to use the second row to eliminate this 8 in the third row. So our next victim in the process is going to be this 8. And what I'm going to do is take -4, row 2 plus row 3. As I'm working this out, let me comment that your row operation, your choice of row operations is not unique. There are other row operations that you could do in different orders. But you would work through a similar process no matter what choice of row operation you made. So here, the first row is unchanged, and the second row is unchanged. But the third row is going to be changed, and it becomes a 0, and then we have -4 plus 1, giving us a -3. And so this elementary matrix, E2, encodes this row operation in the third row, 0, -4, 1. And then identity matrix everywhere else. So notice that my -4 falls into spot 3, 2. That's because this is the linear combination that I'm encoding, involving the 2 and 3 indices. Okay, let's continue on. We're going to have a couple more row operations. So next what I'm going to do is 1/2 row 2. See, I do have something now that's in upper triangular form, which is nice, but I would like it if my matrix looked like it had 1s down the diagonal. So let me take 1/2 row 2. Doing 1/2 row 2 is going to give me 1, 0, 0, 0, 1, and then 1/2. And so E3 will be the elementary matrix that scalar multiplies row 2 by 1/2. So now I don't have any off diagonal entries that are non-zero. I have a 1, a 1/2, and then a 1. The third row is unchanged, and so here we just have a 0, a 0, and a -3. Then there's one more row operation to do, and that's to divide out the third row by -3 so that it's 0, 0, 1. So my third row operation will be 1 over -3, row 3, yielding the matrix 1, 0, 0, 0, 1, 1/2, and then 0, 0, 1. This is in reduced row echelon form. And I have one more elementary matrix to write down. Much like with E3, this is going to be a matrix that looks like the identity matrix, but with one of the entries multiplied by a scalar, and that's going to be the third entry as a -1 over 3. So there are my 4 elementary matrices. And something you should check is that if you left multiply by these elementary matrices, it does the exact same thing as the row operation that we just carried out. So for example, if we take the first elementary matrix, E1, and we multiply E1 times A, that's going to be the matrix 1, 0, 0, -3, 1, 0, 0, 0, 1, multiplied times 1, 0, 0, 3, 2, 1, our original matrix A, 0, 8, 1. what we get out of it is going to be this exact matrix here. This was the result of doing that row operation, and that's what's going to show up here. We should see that we get a 1 plus a 0 plus a 0, giving us 1, and then 0, 0. We'll see here that we get minus 3 plus 3 is 0. 0 plus 2 is 2. 0 plus 1 is 1. And then a 0, an 8, and a 1. And if you check these other steps, it's going to work out that way as well. So the matrix that we ended up with at the end, let me say, is R. R for reduced, row echelon form. And the matrix that we started with was A, and we had 4 row operations and 4 elementary matrices. As a matrix equation, what R is equal to is E4 multiplied times E3, E2, E1, A, where E1A gives me this step. I multiply that by E2 and it gives me this. I multiply that by E3 and so on and so forth. It is extremely important to note that when you do this process, you are multiplying on the left multiplication to carry out these row operations. I hope this explains what an elementary matrix is. I strongly recommend that you work through several examples where you put a matrix in reduced echelon form and you keep track of the elementary matrices along the way and make sure that you get the same answer by doing row operations or by doing matrix multiplication.